Hello, Rouse. For lesson 2.9, I want to talk about the ideas behind implicit differentiation, or the ideas in front of them, and then do another algebraic example with you with a sort of a deeper chain than we've seen. So first off, we've been thinking of the derivative as a separate function that is derived from the first function. In fact, our language goes so far as if we had f of x being this linear function, then we label it a separate function, f prime of x, with separate outputs, f prime x's. That gives us information about the first function. But I want to make sure that we understand that we've always been able to treat taking the derivative of with respect to x as an operation. And that's sort of where this symbol comes from as well. We can say, what I'm going to do is I am going to study small changes of the left-hand side with respect to some very small changes in x, and I'm allowed to do that as long as I perform the same operation on the right-hand side to maintain equilibrium. So I'm going to study very small changes of negative 2/3 x plus 5 with respect to very small changes in x. I'm differentiating with respect to x on both sides. Again, this symbol doesn't really mean derivative of with respect to x. The D doesn't mean derivative of, but we often just sort of read it that way for convenience sake. Now, when you're asked to find the derivative of y with respect to x, there's not much that you can do with it. You could use a chain rule and say this is going to be 1 times y to the exponent 0, and then complete your chain by multiplying by the derivative of y with respect to x. We haven't seen this much because 1 times y to the exponent 0 is always going to be 1, ignoring the case where y is equal to 0. And then we're able to use our derivative properties on the right-hand side. We take the derivative of this term and add the derivative of that term. Okay. So let's not lose track of the fact that differentiating can be thought of as an operation as well. The derivative itself is an output or a collection of outputs called a function, but differentiating can be thought of as an operation. This can be useful because sometimes we don't we use implicit differentiation usually when it's, let's say, difficult or impossible to isolate for our dependent variable. But we can use it if we just say don't want to isolate for our dependent variable as well. Consider lines in standard form. This is the same relationship as this relationship on the left-hand side. But if you ask me to find an expression for the derivative, I do not need to rearrange first. Students that do this, it reminds me a little bit of students that, when asked to find, say, the y-intercept of this function, would feel the need to put it into standard form so that you can see, oh, there's the y-intercept. Well, why don't you just make x equal to 0? Because that's the definition of how you find a y-intercept. Let's just see what implicit differentiation looks like in this case. In fact, it's so important to understand we've been doing this before that some teachers don't teach it as a separate skill. They just say all differentiation is differentiation, whether you're differentiating implicitly or explicitly. Doesn't matter. The derivative with respect to x of 2x, that's 2. The derivative of, let's show a step here. We're taking the derivative with respect to x of 3y. Let's just use our constant rule here. Plus 0 equals 0. And then what we're doing here is maybe constant multiple times the derivative of y with respect to x. Not really much of a chain rule, is it? Now you're going to have to isolate eventually. I'm going to subtract 2 from both sides and then divide both sides by 3. But you can kind of make a choice as to whether you want to rearrange first or differentiate first. And often differentiating is going to simplify your function. So it might make isolating a little bit easier. Good. Let's try another algebraic example. I don't think you'll find it in the notes. You'll find an example like it in the homework. Let's find an isolated expression for delta y by delta x if, let's say, x plus y all squared minus 4y cubed is equal to x. So what I want you thinking about in this example is, do you want to expand, and what advantage does it provide? Maybe I could make this exponent a little bit larger to try to convince you that it's not necessary. That would have other impacts on the question, though. I'm going to start by differentiating with respect to x. I'm going to show my reader that I'm differentiating with respect to x. I'm taking the derivative with respect to x of x plus y. All squared. I guess I'm showing my steps. Minus 4 times the derivative with respect to x of y cubed. This is me accidentally closing that bracket. Equals the derivative with respect to x of x. So that's okay. We'll get some practice with the steps. Here, let's show another step. We're taking the derivative of x plus y squared. That is, power of a variable expression. So let's take its derivative with respect to its base of x plus y. And then complete that chain by taking the derivative of x plus y, the base, with respect to x. Here, I'm going to do the derivative of y cubed with respect to its base, multiplied by the derivative of the base with respect to x. Here, the derivative of x with respect to x, definition, is 1. This is the case where I don't think you would be told to show all of your steps, but students that feel that they're comfortable enough not showing their steps in other questions will sometimes slow down here and find that it's useful, especially the first couple of times they do this. What's the derivative of the square of something with respect to its base? That's 2 times that base to the exponent 1. And then I can concentrate on my chains separately. I've got a derivative of a sum here that's going to be the derivative of the first plus the derivative of the second. Derivative of the first with respect to x is 1. Derivative of the second with respect to x, that's what I'm looking for. So I think this is where some of the problems occur with students using implicit differentiation is they feel like they need to start with dy by dx or f prime of x or something like that. And that's not the case. You're going to discover it. Let's go back up here. You'll discover it in, let's call it, the middle of your expression. In this case, we're going to discover it in a couple of different spots. So we're differentiating with respect to x on both sides. We were told to find an isolated expression for delta y by delta x. Well, there's one instance of it, so I suppose I'm going to have to isolate for that. But I wasn't worrying about where delta y by delta x was going to show up before I got to this point. When I continue my work over here, and I do negative 4 times 3y squared times delta y by delta x, I discover, oh no, I have another instance of delta y by delta x. Which, I mean, it's not a big deal. It does make the algebra a little bit more complicated here. I'd strongly suggest you make sure that you're comfortable with this step, because this step, the differentiation step, is where things can go in a very wrong direction quickly. Right? From here, there's not really any calculus. We just need to use, I'd say, grade 10 algebra to expand and rearrange and factor and isolate. Let's see what that's going to look like. I see some even coefficients, but I don't think dividing is a great option here. I know I'm going to be subtracting a little bit later. I see a distribution of 2 binomials. I think I'm going to concentrate on doing that first, and I'll hold on to this 2 for a sec. I'm going to have x times 1, x times delta y by delta x, y times 1, y times delta y by delta x, y delta y by delta x. We could also tidy this up a little bit to minus 12 y squared delta y by delta x equals 1. I'm not doing anything with this 1. I don't want to subtract it to the other side because I'm trying to isolate delta y by delta x. Having 0 on that side isn't going to be advantageous. Now this bracket is causing me issues, so let's expand through it. Let's try not to do too many different operations on one line for our reader, but I hope that a reader can follow. Let's say subtracting 2x and 2y from both sides, and then removing a common factor from what remains. So here are my terms, my delta y by delta x terms. They're not like terms. Well, they don't have the same coefficient, so I'm not just simplifying the addition of them together. I am removing a factor of delta y by delta x from them, leaving me with 2x plus 2y minus 12y squared. The hesitance in me saying they're not like terms, they kind of are. If you have 2x dy by dx's and you add 2y delta y by delta x's and you subtract 12y squared delta y by delta x's, then you're going to have 2x plus 2y minus 12y squared delta y by delta x's. What else did I say I was doing on this step? I subtracted 2x from both sides and I subtracted 2y from both sides. You might want to count your terms on each step. And I'm one step away from having an isolated expression. I usually won't ask you for a simplified isolated expression because there tends to be a little bit of ambiguity about what simplification is going to look like in these cases. The other prompt I might give you is I might tell you find an isolated expression for delta y by delta x in terms of x and y, so that you feel comfortable having y values in your expression for the derivative, because that was kind of new for this lesson, wasn't it? No. So rewrite the directions, find an isolated expression for delta y by delta x in terms of x and y, and you should feel comfortable with this as a final answer.